Yeah. All right. So last lesson we learnt how to separate integration by separating the parts out. We're going to be doing that again today, but I also want to show you another method as well. So let's just read through the bits first. The logistic differential equation. The logistic differential equation is a first order differential equation of the form y dash equals ky bracket p minus y. Now I know there's a lot of constants in there, like the k and the p, but you'll notice that on the right hand side of that equation, the only variable is y. Okay, so what we're going to be looking at is another way that we can integrate when we only have the one variable in there, which is y. Where the following dot points, assume that p and k are positive. So the constant functions y equals 0 and y equals p are solutions to the differential equation, because if you subbed those in, you would get a solution. The general solution consists otherwise of three groups of solutions. We have solution curves that are going to be between 0 and p with domain all real numbers, and we're going to have solution curves above the p and below the 0. The solution curves in the second group are the upper branches of the two branch functions whose lower branch is a solution in the third group, and vice versa. In applications, one group or even two groups may have no significance. Okay, so we're going to get to a quite large applications question at the end of our examples, which will go through some of those things in there. But first of all, in these first few examples, we want to solve the differential equations using two different approaches. The first approach is going to be the one we did last lesson, which is a separable differential equation. So divide your page down the middle so you've got enough space for both of them. Okay, so first method. A separable differential equation. So we take our equation, and I'm going to write dy over dx instead of y dash is equal to e to the y. And we separate our equation into the y components on the left side and the x components on the right side. So that would be 1 over e to the y, moving that across to the left, with the dy, equals, I would multiply the dx across the other side. Because there's nothing else there, there would be an equivalent to a 1 in front of that dx. Now, before I integrate that, I'm just going to modify it slightly. The 1 over e to the y could be written as e to the negative y dy, because that's going to be easier to integrate. And 1 dx. So I'm just going to put integral signs in front of both sides. Integrating e to the negative y, what do you get? E to the negative y over negative 1, or put the negative out the front. But the process is to leave the power the same and divide by the derivative of the power. And that is equal to integrating the 1 in with respect to x. We get x, and then we add our constant at the end of that side. The negative 1 that I have with my exponential there, I'm going to multiply that across the other side. So I have e to the negative y equals negative x. Now, it would be negative c, but does it really matter if it's a plus c or a minus c when it's a constant? Nope, so let's just leave that as a plus c. Or, to make it look even nicer, we might want to write that as c minus x. Okay, then we want to get the y by itself, so let's slide the base over. It'll be negative y equals log base e, or just ln, of c minus x. And just have to get rid of the minus sign now. So y equals negative ln of c take away x. Okay, so that was what we did last lesson. Hopefully that's familiar and you've had a chance to practice that. Yes, looks familiar. Okay, so now let's look at a slightly different approach. It does have a lot of similarities, but this one is done by taking the reciprocal of both sides. So I'm just going to call taking reciprocals. Okay, so our original question is dy over dx is equal to e to the power of y. Now, the problem is that I can't integrate something in terms of y, I can't integrate with that with regard to x. That's what always the problem is with this. So if I take the reciprocal of both sides, I will get dx over dy equals 1 over e to the y, but a better way to write that would be e to the negative y. Absolute values, yeah. Okay, keep going. Just the absolute values around the, yes, thank you. Put it away, Ben. Sorry, Ashley. Oh, just down here. So we need to put absolute values. That's normally when we integrate, but around here, you can put absolute values around those ones. Let's continue with where we're up to. If I was wanting to get that equation in terms of x equals, I don't need to integrate both sides. All I need to do is integrate the right-hand side with respect to y, because you're multiplying the dy across to the other side and you integrate, correct? To reverse that derivative. Integrating that, we will get e to the negative y over negative 1 again, plus our c. And this is where it's pretty much the same thing from here on out. So we would times our negative 1 across the other side. And then the e to the negative y would be equal to c minus x plus c, or c minus x. Because the c can stay positive, I'm moving the c across the other side, but because it doesn't matter if it's positive or negative, it can stay like that, right? As in the x equals equation? Yeah. I integrated. When you integrate, you're just getting, because it's a constant, it just becomes the x equation. Because sometimes it's easier and sometimes it's not, but it's just more tools that you can use. Sometimes it'll make it easier to do the reciprocal method. Okay, and then, I don't know, it's the same from here. We do it all the same thing again. So minus y equals ln of c take away x, and then move the y across the other side. Okay, try that again. Question 2 says to solve the differential equation again using both approaches. K cannot be equal to 0 because then we wouldn't really have anything to work with. Our equation would be equal to 0. So divide your page in half. Let's do both methods again. So first of all, by separating. Okay, so instead of y dash, we write dy over dx, and that is equal to ky. So we separate so that our y component is going to be on the left, so that will be 1 over y dot dy. And that means I'm leaving my constant on the right, and I'm multiplying the dx over to the other side with it. Yeah? Okay. Then, rather than rewriting it, I'm just going to put my integral signs in front of both of those. And when we integrate 1 over y, we get log of the absolute value of y. When you integrate k, you get kx, good, but we also then add on our constant. Okay, then we want to get out of log form, so we have to leave our absolute value of y and slide our base e across the other side. So e to the power of kx plus c. And we did this last lesson. We then separated that to be e to the power of kx times e to the power of c. At the same time, if I want to get rid of the absolute values around the y, so it's just a y equals equation, I have to put a plus or a minus in front of the right-hand side.
Oh, because
That's right. Could have been plus, could have been minus. Which means that I'm now going to take all of my constants out of there and turn that into a new pronumeral, like b. I've already got a c. I can't use c again. Oh, that's a bit confusing. No. Different letter, please. So I'm going to use b. So b e to the kx. And what I have done is I have replaced b with plus or minus e to the c. Because everything in there is just constants, so I'm just reducing all my constants down into one thing. Okay, so there is my equation. Let's see if we can do that again using the reciprocals method. So starting with dy over dx equals ky. If I take the reciprocal of the left, I have dx over dy equals 1 over ky. Now, because I'm not really integrating any x's, I can make this an integral where x equals the integral of everything on the right-hand side with respect to y. But I'm going to change this a little bit so it's nicer to integrate. I'm going to bring the 1 over k out to the front because that's just a constant. And that way I just have to integrate 1 over y dy. Yeah? So integrating 1 over k is out the front. Integrating 1 over y, we get log absolute values of y. And because we've integrated, plus c. Okay, then we want to get everything back in a y equals form. So subtract the c across the other side.
wait, we're minusing c now. I thought it stays plus.
That is true, but it doesn't actually matter. I'm going to take it all out of there anyway. You can make it a plus if you want to. Because then I'm going to times my k across the other side. And then to get rid of the logarithm, we slide the base e across and it will be e to the power of that k bracket, which I'm going to expand out. K to the x minus kc, or plus kc if you went positive. It's all going to disappear in a minute anyway. To get rid of the absolute values, we're going to have plus or minus. And I'm going to split the exponential to be e to the kx, where my variable is, times by e to the minus kc, where everything is constants. So, like last time, I'm going to change that to be a b, e to the kx, where b is equal to plus or minus e to the minus kc. Okay, and we ended up with the exact same solution curve.
Why did?
Yeah, well, not that it matters, they're all just constants.
What? Wait. But because b is different, the answer be different.
Well, it depends what constant you're putting in, if the k was different for each one.
If you were given the constant, obviously you'd have to start from the beginning again. Then.
Yeah, you wouldn't do both ways in a test. you would pick a method and you'd go with it. So for that one, if you were looking at that, I think the separable way is faster. And a lot of the time I prefer that way. But the first one, about the same. Anyway, maybe a time when the reciprocals might be the easier option.
I'm just.
Okay, you're confused about the second method?
When you got kx and minus kc, why is e kx times e negative kc? Because there's technically.
Yeah, I was gonna say, I can combine all of those constants. I just didn't want to change my constant every single time I timed something together. That's all. So I just saved it all to the end and changed it all at once.
But wouldn't, if you times k to x and k to negative c, wouldn't you technically get two different terms, so there wouldn't be a times sign between the two e's? Instead, there would be a plus sign, minus sign over there.
No, because the whole expression's been raised to the power of b. So the kx.
The e is the base. That's a little kx minus kc. All of that's little up the top. They're all powers.
And when you times powers together, they just plus.
Yeah, so what I'm doing is normally we have the same bases, and when we want to add the powers together, we're reversing that. We have two things in the power that are subtracted in this case, but we're splitting them back apart.
So b is different.
To the first one.
Yeah.
If you remember, I think I changed the sign in that one as well, without noting it as well. Don't let that part bother you. We're just after that's just playing with the constant. We're just after that solution curve. Okay? All right, let's keep going.
But,
Part 3.
okay. So which b would be the correct one?
It's the same. Because when you now work with this equation, you're not even using this little substitution over here on the side. You are now only using y equals b e to the kx. That's it. B is your only constant, and it's just b. We never go back and use k or c at all. It would depend on the question. They'd have to give me some information. And we're going to do that in this next one.
Okay.
So in this next one, we're going to work that out. So question 3. Solve the differential equation. Y dash equals minus 3y given the initial value of y of 2 equals 50. So we've got that information there at the end, but we're going to be able to work out the constant. Okay, so shall we stick with the separating the variables? Okay, so let's go with dy over dx equals minus 3y. Let's move all the y parts to the left. So that will be 1 over y times dy, just moving the y across, equals minus 3 times the dx. Okay, everything has been separated nicely. Now we're going to integrate both sides. So integrating 1 over y, we get ln of the absolute value of y. On the right-hand side, integrating negative 3, we get negative 3x, and we plus our constant. Okay, so this is the same thing again, Ashton. If I want to slide the base over now, so that's a log base e, to get the absolute value of y by itself, I slide the base e across, and the minus 3x plus c is all in the power.
Yeah, no, that makes sense.
Then, in this next line, I've kind of been doing 2 steps. I've been getting rid of the absolute values, which means I want to do a plus minus over here. And now I want to split.
That then told me how to do it.
Oh, okay, cool. So then we want to split the e to the minus 3x times by the e to the c. Okay, then we're going to take all of the constants out. I'm going to call it b again. So it'll be b e to the negative 3x, where we're just saying that the b is the plus or minus e to the c, taking all those other constants away. Okay, now that we've got our basic equation, we can now sub in the point that we were given, which was that when x is equal to 2, the equation was equal to 50. So y is equal to 50. So into my equation, that means 50 equals BE to the negative 3 times 2. Okay, I'm going to leave this exact. Don't go to decimals here. So that's going to be 50 equals BE to the negative 6, which means to get B by itself, you're going to divide the E to the minus 6 to the other side, or that's the same as timesing by E to the plus 6, bringing the power up, right?
Yeah.
So the extra step is that I'm doing 50 over E to the negative 6,
No, I've got it.
and then that brings it up.
It's-
You got that? Okay, so if B is equal to that, then that means that my equation is y equals 50e to the 6, that's the B, times by e to the negative 3x. That's not a very nice way to leave the solution though, because I have a common base of e. Let's push those back together again to be 50e to the 6 minus 3x. Did you get that? Good. Okay, so a lot of questions, you're going to do a lot of that. Okay, there's a lot of questions in your exercise about integrating whichever method and subbing in to find your constants. Question 4, though, is a mammoth question. It is a super big question with lots and lots of parts to it. Lots and lots of things we have to consider along the way. This question I actually think is harder than pretty much anything that's in your exercise. You don't think so? You've done the exercise already, have you? Oh, but I'm talking about in this exercise, not what you're doing. All right, so this question, we are starting with an equation where we want to separate a fraction into two other fractions. Now, normally we don't like to do that. We like to have things simplified. But the reason we need to be able to split it is because the splitted version is things that you could integrate. Okay, we can't integrate 1 over y bracket 1 minus y, but we can integrate the other side. So to show that that rule actually works, all you want to do is you want to start with the right-hand side and just get a common denominator and put it back together again. So my common denominator, I'll just write the right-hand side down first. My common denominator, I would multiply together the y and the 1 minus y. I'm starting with the right-hand side of the equation. I'm going to go back to the left. I can't actually hear you. Everyone's talking. If you want to make it super complicated, this is much easier. Okay. All right, continuing with this. I'm going to multiply the first fraction needs to get multiplied with 1 minus y to its denominator. So 1 times that, it's just 1 minus y. The second fraction needs to be multiplied by y. So 1 times y is y. The minus y plus y cancel each other out. And there it is, 1 over y bracket 1 minus y. So I've shown in a couple of lines, that's equal to my left-hand side. I've shown that those two things are equal to each other. Okay, that's all I had to show in that question. Part B. Hence, I want to solve the differential equation, writing the solution with y as the subject. So my differential equation is dy over dx equals y 1 minus y. Now, if we're going to use the separable method, let's get all of our y parts over on the left-hand side. So it's 1 over y times 1 minus y dy equals, now there's no x parts left there, so it's going to be 1 times the dx. Now, hopefully, this part here looks really familiar because we just in part A separated that. And we need that separated so that we can integrate it. So let's change that to be an integral but instead of integrating what's there in yellow, let's replace it with the separated version, which is 1 over y plus 1 over 1 minus y dy. And then we're also integrating the 1 with respect to x. Okay, integrating 1 over y, we get ln of absolute value of y. Integrating 1 over 1 minus y, we're going to get log of 1 minus y, but because the derivative of 1 minus y is a negative 1, it means you need a negative 1 out the front.
Or is it just copying?
I will do an extra line. Let me do an extra line. All right. To do the extra line, to integrate that second one, you need the derivative of the bottom to be on the top, correct? So that means I need a negative 1 on the top, which means I've got to compensate for that minus 1 by putting a minus at the front, which is what I was doing. Yeah? All right, so there you go. Adding that extra line, and that's all right. Yeah, so then we have ln of absolute value of y minus ln of correct. And integrating 1, we get x, and don't forget your constant. Okay, now log subtracted, log laws, means that you can combine those two logs to be the absolute value of y over 1 minus y. Log laws, hey, language, this has been recorded.
The freak.
Still. Okay.
By. What the? Yeah. I shall. Sure.
Yes, make sure you don't say anything that even sounds inappropriate.
It's so weird. People get offended by everything he says.
Okay, next step. Get rid of the logarithm. So slide your base across. So we have y over 1 minus y. It will be e to the power of x plus c. Get rid of the absolute values. So we have y over 1 minus y equals plus or minus e to the x times e to the c. Now I am going to just get rid of all those constants and call it a e to the x or b e to the x. Lots of different letters you can put in there. Where a is equal to plus or minus e to the c. Now remember though, we needed to get an equation, it's said in part B, with y as the subject, just y. Now at the moment, I do have all the y's over on the left, but not, I've got multiple y's, correct? So I have to try and collect them up. What you want to do is you want to times your denominator across the other side. So it's going to be y equals 1 minus y times a e to the x. When you expand that out, you will have a e to the x minus y a e to the x. Then you want to get both of your y terms over on the left so you can factorize the y out. So you're going to have y plus y a e to the x equals a e to the x. Everyone still with me?
Yes.
Factorize the y out and we have 1 plus a e to the x equals a e to the x. And finally, y all by itself would be a e to the x over 1 plus a e to the x. However, if this was the textbook, that would not be the solution because they do not want to have two different constants in, or not two different, but the constant in there twice in your equation. So instead they would want to divide that whole equation through by a e to the x, try and simplify it down further. So if I divide by a e to the x, on the top, a e to the x divided by a e to the x is just 1. 1 divided by a e to the x, I'll actually write it down, it'd be as a fraction, 1 over a e to the x, but I'm going to fix that up in a minute. AE to the x divided by AE to the x is again just 1. So the only part, this bit in here, is a little bit messy still.
Doesn't that A to the X go to the top?
I'm going to take it out of a fraction, yes. So in that little highlighted yellow part, the 1 over A is just a constant. So yeah, what I'm going to do is I'm going to change this. Oh, not with the highlighter. I'm going to change this to be a B. Okay, the 1 over A, I'm just going to change that to be B, just the 1 over A part. And the E, I'm going to bring up the base to be e to the minus x. I can't because of the 1.
1 over 1 plus 1 over 1.
And then flip it upside down? You should get the same thing. Yeah? Possibly.
No,
if you work it through. Yeah? Should get the same thing. You can work that one through.
So
See if you get the same thing. So it should be a plus 1. So that is it. You can make a little note there. What I've done is I've said that B is equal to 1 over A. Okay, so it's that extra constant change again. I was taking the 1 over A out and just replacing it with the letter B. Okay, so here is my equation so far. I'm only subbing one constant in. It's only going to be one constant. Nope. No. All right, so let's keep going. Part C. Because here it is. This one here, look at it. Yeah, oh, there's like F. This goes to F. It's a long question. That's why I said it's a big question. Oh, no. The whole next 3 pages are all on this one question. It's a big question. Dude. So now there's part C. So here it is. I told you this was a big one, and it's a very involved question. We've still got a fair bit to go. In part B, we found the general solution. So that was the equation that I gave you. I think I just had my denominator switched around, but that's okay. Which is a solution of my differential equation. Use this to find the connected solution curves through, and we're going to have 3 different points. Because remember, thinking back to those lovely field diagrams, I guess they do have a purpose because we're visualizing all this stuff. You do have different types of curves that can be made in different places, right? So here we have the point 0.5. First thing we do is we sub it in. Let's find the new equation with that. So sub in 0 and 0.5 into that differential, the yellow equation. We're going to get half, or 0.5, equals 1 over 1 plus B, and then it should be e to the power of negative 0. But what is e to the power of negative 0? Or just 0?
0.
It is just 1. Can't be 0, would be in trouble.
That was a dumb mistake.
So I don't need, the exponential part is all just equal to 1. So it can just stay as 1 over 1 plus b. All right? Then I can do some cross multiplying. 1 times 1 plus b would be 1 plus b. And 1 times 2 is just 2. And that means that b is equal to, subtract the 1 across, b is equal to 1. Then I get... Yes, we don't need that. Yes, try not to dwell back there on those other bits. Okay, that means the solution for this part of the curve is 1 over 1 plus b is just 1, so e to the negative x. Okay, that is my equation. Now, what do I know about this equation? Because there's a lot more stuff coming. I need to know some things about it.
C.
We didn't need it. It was all about x and y. And you determine the constant based on the things you substitute in. Great. So in here, I'm going to draw a little sketch of this. What is the domain of that curve? Is there any restriction to the x values that I can put into there? No. I can even put 0 in. I can put any negative value in I want, any positive value in I want. So all real x. So there's no problem with that. What about the range? What possible y values could I get by subbing any x values I want into that? If I were to sub in really small values for x, so like negative infinity, we love those ones, negative infinity, negative big numbers, e to the negative negative, so positive, e to the positive infinity is going to be massive, right? Plus 1, still massive. So it's going to be approaching 0. Okay? No, it's a positive infinity. Positive infinity plus 1 is still a very big number, and 1 divided by a big number is approaching 0. That's actually the smallest value that curve can ever get to, 0.
It goes to 0 positive side.
Then think of going to positive infinity if you subbed e to the negative infinity, because we're putting it minus. The e to the negative x is approaching what? No? 0. Just this bit. I'm trying to work out what that part there is. Okay, that e to the negative x, e to a negative big number is really, really small. Okay? Then when I add 1 to it, it's pretty much 1 on the denominator, and 1 divided by 1 is 1. So my range is actually between 0 and 1. Now, this is what I've done. Actually, this is some working out. Put this down on your page. Limit as x is approaching infinity. This is what I was doing. It makes more sense on your page. If we sub that into our equation, we're going to get 1 over 1 plus e to the negative x. And when we put the positive infinity in, that was when it was going to 1. If I do a limit as x is approaching negative infinity into that same thing, that one is approaching the 0. So it actually means it is when you're subbing in negative infinity, it's going to 0. So on the negative side. It is an asymptote. So I was just about to write it. Y equals 0 and y equals 1 are asymptotes. They are approaching, but they will never get there because technically that exponential part can never actually reach 0 or 1, but it would get really, really close to it. Okay? So, I know this is going into the next question a little bit, but let's just draw what we've discovered so far, and we'll add bits to it as we do the other three parts, 3 in total. We have discovered at 1, we have a horizontal asymptote coming through there, and also at y equals 0. The point that we subbed in was at 0.5. It's right in between. And as we went to negative infinity, it was approaching the 0 asymptote. So it's coming down and it's approaching that 0 asymptote as I go that way. As I go to positive infinity, it was approaching the 1. So it's coming up and going that direction. Okay, so as you can probably tell though, why do I have 2 more points? Because I'm now going to see what's happening above in that graph and below. So let's sub in our next one. If I want to sub in the point 0.02, let's sub it into the original equation that is up the top of the page. So y is equal to 2 equals 1 over 1 plus 1 plus b. Yes, correct. So let's time, like I did last time, times the denominator over to the other side. So it'll be 2 times 1 is 2, plus 2 times b is 2b is equal to 1. Then 2b is equal to, subtract the 2 across, and I get negative 1. And b is equal to negative a half. So this equation, different equation, right? B is different now. So the solution curve is y equals 1 over 1 plus b, but b is negative a half, so minus a half e to the negative x. Okay, that. I'm going to draw that one now. What do I know about that graph? Actually, no. First of all,
Did we sub in did we find a different b value because it's technically a different graph?
yeah. Do you remember drawing those slope fields where we had 3 different types of curves? And we're going to have that in this one here. Okay, first of all, because I have a minus sign on between my 2 terms on my denominator, that means it actually is possible to make my denominator 0. There will be a vertical asymptote. So the vertical asymptote is going to be when the 1 minus a half e to the minus x is equal to 0, right? Let's find where it is. Let's move the half e to the minus x to make it positive, so that's equal to 1. Then we're going to times the 2 over to the other side, so e to the minus x is equal to 2. And then what do I have to do with that? To get x, slide the base. So minus x is equal to log base e, or ln of 2. Yeah, and move the negative across. So minus ln of 2. I have a vertical asymptote. Okay, where does that vertical asymptote exist though? Yeah, that's the value of log 2. The initial value that I'm working with, the initial value is that x had to be equal to 0. Okay, that was in my point. It was the point 0.02, right? If x is equal to 0, L minus ln of 2 is, it's bigger than that, right? The x value is bigger than that asymptote. So my x values are bigger than the minus ln of 2. Now, because it has to be bigger than that, means we're not going to have any negative infinity things happening in here. We know we're going to be starting at that negative 2 asymptote, and we want to see what is happening as we go out to positive infinity. So let's check it with our limit again. Okay, you can do some of this stuff in your head, but this is a reminder on how you show it. Because it said the part of the curve that I am looking at says that x is equal to 0. Okay, and that means if my asymptote is at minus ln of 2, which is minus 0.67, something like that, 0 is bigger than that. I'm looking at the x values that are bigger than that. Okay, I'm not looking at anything to the other side. I just want that particular side of that curve, which, by the way, this would resemble some kind of very unusual hyperbola, but we only want one portion of it. Okay, so we want to now sub in the limit as x is approaching infinity into my yellow equation there. So that's 1 over 1 minus half e to the minus x. Now, if I am putting infinity into the e to the minus x, it is approaching 0, correct? Which means half of 0 is pretty much still 0, and 1 minus 0 is just 1. That whole thing boils down to basically being 1 divided by 1, which means that it's approximately equal to 1. That means it is approaching 1. That's the y values. But because it's getting bigger, it'll be above the 1. So on the graph, the question wasn't asked to do this, but it's going to make it easy when we have to analyze this later on. This point that we just did was the point 0.2. So 0.2 is going to be here. We discovered that we had a vertical asymptote at I'm going to draw, it's only for certain values though. So we're looking, this goes through minus ln of 2. That was where my vertical asymptote was. As my x values are going out to infinity, my curve is coming down and approaching 1. Hey, that's where my horizontal asymptote is. My curve is coming down and is approaching like this. What do you think it's doing as I get close to my vertical asymptote? It's going off to infinity. So you could sub in values, you could do another limit if you wanted to confirm that, but it would look something like that. All right, we still have to analyze what is happening below that graph now. So part 3. Part 3 is, we are now subbing in the point 0, -1. So let's sub it into our original equation. It's good, all the x values are 0, right? So it makes it easy. We have -1 for the y value equals 1 over 1 plus b e to the 0. The e to the 0 is still just 1, so we just have that nice little equation. Times the denominator over. We get -1 minus b is equal to 1. Then adding the -1 over, we get negative b equals 2. Dividing by the negative b equals -2. Then we have our solution curve, which is y equals 1 over 1 minus 2e to the minus x. So here is my third curve. Okay, same kind of thing. What on earth is that curve doing? How do I put it on my diagram? It is also going to have a vertical asymptote. Because of that minus sign, I can make the denominator 0. So let's find it. What did you say? No, it's positive. Vertical asymptote is when the 1 minus 2e to the minus x is equal to 0. The denominator equal to 0. Which means if I move the 2e to the minus x to be positive, that would be equal to a positive 1. Divide the 2 across the other side, which I'm going to be a little bit sneaky here, and 1 over 2 is a half, or 2 to the -1. You can do a half. It's going to set me my logarithm part. I'm setting up for my log. Because now I want to slide. So this is e to the -1/2 is equal to a half. But rather than writing it as a half, I'm writing a half as 2 to the power of -1. Just bringing the base up. Because when I slide my base now, I'm just going to delete all that because there's already too many things happening in there. If I slide my base, I keep my minus x, it's going to be log base e, or ln, of 2 to the -1. So now that -1 is perfectly placed to bring the minus down to the front using the third log law. It's minus ln of 2, which means divide the minus out and it becomes x equals positive ln of 2.
So
Oh, it's just, okay, just not as simplified. Sorry, I thought you said minus ln of 2. Okay, just simplify it further and you'll be there. Okay, well, what x values are we looking at for this one? My x value was 0. Is 0 less than ln of 2 or greater than ln of 2? It is less than, okay? So because, or as, my x value is equal to 0, that's what I subbed in. Because this was the initial value, that means that x is going to be less than ln of 2. ln of 2 is 0.67 and 0 is less than that. So that means when I'm talking about my asymptote, my vertical asymptote this time, which side do I want my curve on? The left. I want to be going to negative infinity this time to analyze what's happening. You probably know what's going to happen already. But, all right. If we do a limit as x is approaching negative infinity, all right, before I do it, let's come back here. I'll show you my diagram. So on the diagram, we have got a point was 0, -1, so that's here. There's my -1. I've just discovered that I have got a vertical asymptote here at ln of 2. Okay, and we want to know where the rest of the curve's going to go. So pretty good bet. You can probably just tell by me drawing that much, do you know where the rest of the curve's going to go? It's going to approach this asymptote down here, and it's going to come up close up there. But I was just confirming that approaching negative infinity part. As I go out to that negative infinity, I was just going to confirm that with my limit. Okay, so let's just confirm that. Where is that? Here it is. My limit as x is approaching negative infinity, if I sub that into my 1/1 minus 2e to the minus x, what am I going to get? Now, if you're putting negative infinity into there, the two minuses become positive, so it's e to the positive infinity, which is massive. 1 minus massive is still massive, right? And 1 divided by infinity is approaching 0. Technically, it would be on the lower side of that because it would be negative, because it would be a negative massive number. What did you sub in for your x? Negative 10,000, I'll let you do that. It should be a plus. Because you're subbing in negative infinity with a negative sign, it should be a plus. And then your calculator goes, too big, can't handle that. Yeah. So what that conclusion, we have a horizontal asymptote at y equals 0. No surprise, because we already had that asymptote. And our y values are going to be less than that. And we can see that on our curve. Our y values are all less than that 0, than y equals 0. Right? And that is the 3 solution curves that we've been given to work with.
Still got 3 questions.
Yeah, which are to do with describing stuff, which we love. All right. Okay. Part B. How are the solution curves to C part 2 and C part 3 related?
There was C. C.
These are the C was the ones where we subbed in the 3 points. Yes. Remember I said that the part 2 and part 3, they are actually hyperbolas, and we have just taken the part of the hyperbola that had our point in it. There would have been another part of the top green hyperbola. There would have been another part to it coming down this way, right? But it just wasn't where my point was. It wasn't part of my solution curve, right? So that's kind of what I'm going to describe. The same thing happens to the bottom one. I'm just taking one part of that, and it would have another partner as well. Let me write it down. Okay, so in part 2, it has a disconnected branch to the left of x equals minus log of 2. Okay, so we had the part to the right of it, but there would have been a part to the left of it, which would have been below. So this branch would have been below the y equals 0 line. And the reverse happens for part 3. It has a disconnected branch to the right of x equals ln of 2, which would have been above the y equals 1. So in general, each solution of the differential equation above y equals 1 is paired with a solution that is below the y equals 0. Okay, so yeah. Okay. Two more parts, E and F. Did you get all that written down? Sorry, Logan, did you get that?
My watch is even telling me to walk.
You need to write faster and keep your hand moving.
So I'm going to take a bite.
All right. Okay, part E. Consider y dash equals y bracket y minus 1. That's our same differential equation. Prove that y double dash equals, and we have two different things there that we have to show. So if I want the second derivative, that means I have to differentiate, so d over dx, I have to differentiate this thing here. But if I'm going to differentiate that, I'm going to expand it out. So when I expand it out, it's going to be y minus y squared. Okay, so I'm going to differentiate y minus y squared. Now, I can't differentiate with respect to x something that is in terms of y, right?
Yes.
So I'm going to have to do some fancy chain rule stuff in here. I need to change that to be a d over dy so that I can differentiate the y's that are in my equation here. And in order to compensate for what I've done, I will multiply by a dy over dx at the end. And if you think about it, don't cross this out on yours, but the dy on the bottom of that would cancel the dy on the top of that one, and there's my d over dx, which is what my question was. As in the line above was d over dx. All I've done is change it to a d over dy times by a dy over dx. The dy's would effectively cancel out, which is why it's equivalent to a d over dx. Do you see what I'm saying? Okay, so I can do my derivative of my y. I can take, I'm going to try and delete those red bits now. Oop, almost did it without deleting other things. I'm going to take this first part. I can differentiate that with the d over dy, right? So differentiating, I get derivative of y is 1, derivative of y squared becomes negative 2y. I have not used the dy over dx that is sitting on the end. I just differentiated with respect to y, which was the one that was at the front. The dy over dx is otherwise known as a y dash. Y dash is a dy dx, right? So I really have y dash times by 1 minus 2y, and that is this first one that I had to show. Then to get to the next one, correct, Ben, good job. To get to the last part of that line, I then need to sub in what y dash is equal to. Y dash is equal to y bracket 1 minus y. So if I sub that in, the y dash is replaced with y bracket 1 minus y, and then I have the 1 minus 2y that is sitting after it, and I have my third part of that.
I actually really like it.
Oh, you liked that? Oh, good.
It just fell together. It just perfectly worked.
All right, now you got to analyze it. Part F. This is the last part though. I told you this was a doozy of a question. Okay, part F. Use this result and the differential equation itself to analyze the gradient and the concavity. Remember, the first derivative is the gradient, second derivative is concavity of the solution curves in parts C, 1, 2, and 3. Probably not going to quite do that, but we'll talk about it a bit. All right, so we're going to talk about the gradient and the concavity. I just want to focus on that part. So first point, the first differential equation, all right? The first derivative, I'm going to use the y dash equals y1 minus y. And I want to analyze what is happening in that differential equation. If I had to draw that, now I'm not drawing an x versus y graph, I'm drawing a y versus gradient graph. I would have zeros from here. I would have zeros at y equals 0 and y is equal to 1. This is just to help me process what's happening. Okay, I need to make some comments, so I need to know what's happening here. So that as a curve of y on the x-axis versus the first derivative. Hey, we've already discussed that. 0 and 1 are my intercepts, 0 and 1. Treating this just like it was a normal polynomial, the y times negative y would be a negative y squared, so it's going to be a concave down parabola. So it would be coming down like this. Okay?
Some y dash equals.
No, because that was one of my zeros, so give me the 0 again. Oh, y dash equals 0. Oh, that's exactly what I've done to get those zeros.
We find the y double dash to find the.
Now remember that this is a sketch of the gradient, right? So anything between 0 and 1, my curve, my gradients are positive because it's above the axis there. So you are going to have all positive gradients, which means that the curve is always increasing between 0 and 1 for y values between 0 and 1, right? So let's write that down. So this tells us that y dash is positive for y values that are between 0 and 1. And we kind of knew that when we did that little sketch, right? Remember the middle part between 0 and 1, my curve was starting down at the 0 and it did a little wiggle, but it was increasing the whole way up to the 1, right? What happens when I am less than 0? My gradients are negative, which means my curve is decreasing. And the same for when y is greater than 1. Also negative gradient, which means decreasing. So it's going to be negative for y is less than 0 and y is greater than 1. Were both of our curves decreasing in those sections? I hope so. Okay, so hence the middle section is always increasing and the outside sections were always decreasing. What about the second derivative? We were asked to talk about the concavity, and that's the second derivative. So the second differential equation was that y double dash equals, I'm going to use the completely in y equation, which is that one. So along the same kind of track, if I want to investigate the concavity, I could look at the sign being positive or negative of my second derivative of that curve, if I can draw that curve, which I can. What are the zeros of that curve? Yeah, so 0, so y equals 0, y equals 1, and y is equal to a half. As a little sketch, this is all just thinking space. We have 0, half, and 1. Now, this is thinking back to polynomials. That's a cubic. We have a positive y, a negative y, and a negative y. So that would be a positive y cubed when you times that all out. If it's a positive cubic, which way do the arms go? Yep, positive on this side. So up, down through here, like that. Okay, I didn't have to sub anything in because we know what shapes our polynomials make. Because I times in the y values together. Because a positive cubic. Yes. Yes, you have to word it like that. It sounds confusing. But yes, it is a y versus concavity. Because what this is showing us, wherever it's usually my y values, but everything above the horizontal, I'm going to call it the horizontal axis to save confusion, everything above the horizontal axis is positive, right? What does positive concavity mean? Concave up, happy. So between 0 and a half and greater than 1, the curves are going to be concave up. No, because it is still an XY. It's still this is. I think you're way overthinking it. Yeah. Let's write this down first and we'll go back and relate it to our graphs. So, all right. So this tells us that y is concave up between 0, or not equal to, sorry, there shouldn't be an equal to sign there, 0.5. And y is greater than 1. And it is concave down because negative concavity between, so that's neg for negative, when y is less than 0 or when y is between 1/2 and 1. Neg for concave down because it was negative. What this is telling us is that there is a change in concavity. Where's the change in concavity? At that half. Remember we subbed in half was one of our values? And there is a change of concavity from positive gradient down to negative gradient. So therefore, in the middle region, there is a change of concavity at y equals 1/2.